welcome back to the channel. Today we will be continuing our discussion on laws of motion and we will be taking up the third law of motion, Newton's third law of motion today. Now Newton's third law of motion is probably the most commonly used in the colloquial language. Every action has an equal and opposite reaction. What does it mean? So first of all, let's consider an object A and another particle, say B. So what it says is that if A exerts certain amount of force on B, say in this direction, F B A, force on B due to A, then B will also exert a force in the opposite direction, F on A due to B. And these two, by definition of third law of motion, are equal and opposite. That is to say, F AB, force on A due to B, is equal to F BA, but minus of it. Which means that forces do always exist in pairs. That is contact forces. If two objects are in contact, then they will exert force on each other, and these two forces must be equal to each other and opposite to each other. Number one, forces exist in pairs, contact forces. That is when objects are in contact. Number two is that these two forces, one can be called the action. A's force on B, if we call this action, then B's force on A is the reaction to the action. Then this action and reaction do not apply on the same body or apply on different bodies. Why not on the same body? Let's say this is the body where action is applied here, F action, and F reaction is applied here. So two equal and opposite forces apply on the same body, then the net force will be 0. And so there will never be any motion, which means that if I take this pencil and push it, if the action and reaction were at the same point, the push will not accelerate the body. Why it moves is that the force applied by me and the force applied by the pencil back on me, they are equal. However, my hand is much more massive compared with the pencil. That's why the pencil bounces off, the hand doesn't. But I always feel the force on it. If I hit the hand with the pencil, it rebounds. You can see the pencil rebounds, my hand doesn't, because it's much more massive. So the effect of the pain on it is less because of the inertia of the hand. Another thing you can see that when you are standing on the ground, say, so you are applying force due to gravity, mg, and the ground is also applying a force on you in the upward direction, which is known as the normal reaction, and this R is equal and opposite to force. That's why you do not sink into the ground, because the reaction force, the contact reaction force due to your weight or against your weight on your feet towards upwards direction balances the weight of yourself. If there were no force, you are released in the space, you will accelerate downwards, as you know, will fall, right? Okay, now if a force of FBA, force on B due to A, is applied on B, then we know that it will produce a change of momentum in B, and if PB be the change of be the momentum of B, then FBA must be equal to dPB by dt. Newton's second law of motion. Similarly, FAB must be equal to dPA by dt. Rate of change of momentum is equal to the applied force. right? So if we add these two, FAB plus FBA, we are applying Newton's second law of motion to the action and reaction pair. So what we get, dPA by dt plus dPB by dt, which is equal to d dt of net change of momentum. However, in this case you have noticed that these two forces, contact forces, are forces exerted by one on the other. There is no external force being added to it. No external force means, by second law, if F external becomes equal to 0, then change of momentum as given by this must be equal to 0. If there is no external force applied, then change of momentum must be equal to 0, or we can say that FAB from this is equal to minus FBA. So you can consider this as the proof of third law of motion. You can also see that third law of motion is not actually a new law. It's just a corollary of second law of motion. As you have seen in my earlier video, that first law of motion was also a corollary of second law of motion. That is why Newton's second law of motion it contains first law and the third law also. So if we consider it that way, that Newton actually propounded a single law, second law of motion. Both first and the third laws are basically corollaries of it, and that is why second law of motion is known as the real law of motion. Because this is the master law based on which we can always find first and the second law. How it is related to the first law, you can always refer to my previous videos where I have explained how second law gives rise to first law, or first law is actually contained in the second law. Okay, alright. Now let's move to a very old problem or very old example of third law of motion, and we can see how it can be applied to the real life, which is known as the horse and cart problem. What happens is that, forgive me for the drawing, a horse is tied to a cart, say, through a string or a rod or something. Now, under what condition the horse will be able to pull the cart forward? Okay. Now say mass of the horse be M and mass of the cart be capital M. Okay. So what are the different forces that will be acting on it? First of all, if the horse wants to pull it, what will it do? Pull the cart, what it will do? It will basically press the ground. It will not press the ground downwards, but it will press the ground downwards and backwards. So let's say the horse applies a force like this on the ground. Let's say this be the force by the horse. So there will be a normal reaction to it. There will be a reaction to this force by Newton's third law of motion, and that reaction will be equal and opposite and will be in this direction. Let's call this R. Okay. So this reaction will have two components. One is the horizontal component and the other one is the vertical component. Let's call this H and V. Okay. Now there will also be another force on the horse that will be in this direction, and this force is the weight of the horse, M into G. So what we see is that the force applied by the horse in the backward and downward direction will give rise to a reaction force due to Newton's second law of motion or third law of motion. And this reaction we can divide into two components. One is the vertical component, one is the horizontal component. The vertical component is going to balance the weight, as we have just discussed, that you are standing on the ground because your weight is balanced by the upward force, reaction force, right? Second is that this force, horizontal component of this force, will try to pull the cart forward. Now, since a force is applied on this particular string, so there will be a tension that will be developing in the backward direction, and this will also pull the cart in this direction. These two will have the equal magnitudes, and in the case of any string, if you apply force tied to one end and apply force in one end, the other end also will exert the same force in the same direction. So this string tends to pull the horse backwards, and horse tends to pull the string or the rod forward. So if I consider the horse, the net total horizontal force will be H and T, right? So if H is greater than T, that is the force, horizontal component of the reaction force is greater than the tension in the string, then H minus T will be equal to M into A, where A is the acceleration of the horse. Okay, now if I consider the mass, or sorry, the cart, what will happen for the cart is that the cart, there is one force T which is trying to pull the cart forward. There will be another force here on the wheels of the cart which will tend to stop it. That force will be known as the friction, right? We will discuss friction a little later, but we know that since the cart is on the ground, so the ground will resist any motion between the wheels of the cart and the ground, and that's why there will be a friction that will be generated at the contact point. So for T greater than F, this is for the cart, we get T minus F is equal to capital M into A, because the cart and the horse will have to accelerate with the same acceleration. We cannot have different accelerations. Now why we have said that for H greater than T? If H is less than T, what will happen? If H is less than T, then H minus T will be, if H equal to T, then it will be 0, H minus T will be negative if H is greater than T. Oh sorry, H is less than T. Then the cart will not move forward at all. H has to be greater than T for the cart to accelerate. Net force must be in the forward direction for the horse to accelerate. And similarly for the cart also, the net force, F is the backward direction force, T is the forward direction force, as we have seen here. So this net force must be forward, and the acceleration of both of them must be equal. Now if we add these two equations, what we get? We get, sum of the equations will give us H minus F, because T and T will cancel out, will be equal to M plus M into acceleration. Therefore, acceleration will be given by H minus F by M plus M. That is to say, the acceleration of the cart will be basically dependent on the horizontal component of the reaction force to the horse's force, which is of course equal to the force exerted by the horse, the reaction horizontal component, and the force of friction. If therefore the acceleration will be greater than 0 or will be positive, or there will be an acceleration in the forward direction if and only if, or the horse and cart system will move if and only if, that is if we have H greater than F. If H is not greater than, or horizontal component of this force is not greater than the frictional force, because friction is a self-adjusting force, please remember this. If H is less than, not greater than frictional force, friction will adjust itself to the H so that the object doesn't move forward or backward, it will remain same. As the H keeps on increasing, friction will also keep on increasing. There will be a point where H becomes greater than F, then only the cart will start moving, otherwise it will not. We have already seen that if you try to push something, it becomes very difficult to push it. Initially you have to start applying more and more force, and after a certain point only it starts moving. So the force needs to keep on increasing. Friction also balances it till the friction can no longer contain it, and then only the object will move. So the condition for the cart and horse to move is that horizontal component of horse's force must be greater than that of F. This is a very nice and beautiful example of Newton's third law of motion. Okay, let us now consider the case of apparent weight. Let us consider at the very beginning that a person is standing in a box. The box is not moving at all, or it's not accelerating at all. That is, acceleration A equals to 0. It could be stationary or it could be uniform motion. There is no net force on it. Then what are the different forces that is applying on it? Is simply on the man is the man's weight downwards, that is m into g, and then there is a reaction force due to this weight which will be in the upward direction. Sorry, you take this pencil. In the upward direction, whose magnitude is say r. Then if there is no acceleration, we must have r equals to mg. This is the normal case when you are standing on it. So if you put a weighing machine on it, your weight will be measured to be equal to the normal reaction given by the weighing machine on it. That's how you find the weight. Now what if the whole setup is moving with an acceleration A upwards? Even then, the weight of the man will still be m into g. However, since it's moving upwards, there should be a net upward force. That net upward force will be in this direction, and that will be the reaction force now. So what we will find is that for this equation of motion, there should be upward acceleration, upward force minus the downward force of weight must be equal to mass into acceleration, which gives us r equal to m into g plus a. So what will happen is that if you put a weighing machine under the feet of a person who is accelerating upwards, what will happen is that he will have a total acceleration, or his reaction force will be mg plus a. So there will be an additional acceleration, amount of acceleration that he will experience. As a result, the force of reaction that is measured by the weighing machine will be larger. In other words, the apparent weight is higher. So when you accelerate upwards, your weight as shown by a weighing machine will be higher than your actual weight. By how much? Mass times the acceleration with which you are going upwards. Similarly, if you go downwards with the same similar acceleration, then you have this mg here. This time r has to be smaller. Why? Because now the equation of motion will be mg minus r must be equal to ma, the downward motion. R is upwards, the force is downwards, the acceleration is downwards. Or we can say r equal to m into g minus a. In this case, apparent weight will be lower or less than your actual weight. What if you move downwards, if A becomes equal to G downwards? What if you move downwards and your weight, your downward acceleration is equal to acceleration due to gravity, and say R is the normal reaction? Then we must have mg minus R, because downward acceleration must be equal to m into g, because acceleration downwards is g now. That is to say, R will be equal to 0. which means if an object or a person or something is falling freely under gravity, it will not feel any weight. So the weight of an object depends on the state of acceleration of it. If there is no acceleration, you get the true weight. If there is an upward acceleration, your apparent weight will be higher. If you have a downward acceleration, then your apparent weight as given by the weighing machine will be lower or less than your actual weight. And if you fall freely, or if you jump from a particular height, or if you drop something from a particular height, then the weighing machine and the object on it is moving with an acceleration equal to the acceleration due to gravity. Under such condition, the weighing machine will read 0, which means a free falling object doesn't feel any weight.